Welcome to This Explainer. Today, we're diving straight into the fascinating mathematical framework of reinforcement learning. We're going to be looking at a really groundbreaking 2026 Princeton dissertation by Zihan Ding titled Reinforcement Learning from Algorithms to Foundation Models. We're going to unpack exactly how artificial intelligence actually learns to make decisions. And maybe more importantly, we'll see how researchers are training AI to become mathematically unexploitable in super competitive environments. It's really wild stuff. Okay, here's our roadmap for today. We'll start with a quest for AGI, then look at single-agent reinforcement learning. After that, we'll enter the opponent, dive into the Nash equilibrium, and wrap things up with unbeatable AI strategies. Let's jump right in. Section 1. The quest for AGI. At a conceptual level, reinforcement learning perfectly mirrors the kind of incentive-driven adaptation we see in human neuroscience, like dopamine signals. This profound quote from the dissertation really hits the nail on the head. Instead of writing millions of lines of code prescribing exactly how an AI should behave step by step, we just specify what it should want. We guide it by defining its desires through a reward function. From there, the AI has to figure out the absolute best strategy to grab that reward all on its own. Moving right along to Section 2, Single-Agent Reinforcement Learning. The very first piece of this puzzle is the agent and its policy. You can basically think of the policy, which is represented mathematically by the Greek letter pi, as the agent's internal rulebook. It's the mathematical decision-making rule that looks at the current state of the world and says, okay, based on this, here is the action I need to take next. Now, once the agent actually takes that action, the environment responds, and it does this based on its own internal dynamics. The agent doesn't control the environment, right? It can only interact with it and kind of wait to see what happens. The environment then feeds back two absolutely crucial pieces of information: a new state and an immediate reward. This completes a continuous trial and error loop. Over time, as this loop repeats, the agent updates its policy, rulebook, to maximize the total long-term cumulative reward it gets from these interactions. It's literally learning by doing. To formalize this whole loop, the author introduces something called the Markov decision process, or MDP. An MDP is essentially the mathematical engine driving this entire single-agent learning process. What's so elegant here is that it ensures the future depends only on the current state and action, completely ignoring the entire history of how the agent got there. So, what are the exact ingredients making up this MDP framework? Well, we have S for the set of states the environment can be in. A stands for the possible actions the agent can take. P is the transition probability, basically the odds of landing in a specific next state. Then there's R, the reward function. And finally, we have gamma, which is the discount factor. Gamma is super important because it tells the agent how much to value immediate rewards versus future delayed ones. That brings us to Section 3. Enter the opponent. So what happens when the environment actually fights back? Single-agent RL is a lot like a solo puzzle game. The environment doesn't strategically respond to your behavior. But multi-agent RL, that's more like a highly competitive chess match. Your opponent is actively adapting to exploit your weaknesses. Because of this massive shift, a single optimal policy just isn't enough to survive anymore. Your objective fundamentally shifts from simply maximizing a reward to finding an equilibrium. To mathematically model this competitive landscape, the dissertation expands that basic Markov decision process into what is known as a Markov game. So now we're incorporating multiple players, joint actions, and often directly conflicting rewards. The state of the game evolves based on what everyone is doing simultaneously. It's a whole new ballgame. Which leads us perfectly into Section 4, the Nash equilibrium. In specific two-player zero-sum Markov games, one player's gain is exactly the other player's loss. Literally, if I win a point, you lose a point. Game theory resolves this intense dynamic through the famous Nash equilibrium. It's a stable state where you are playing your absolute best response against your opponent's absolute best response. Think of it this way. If you are in a Nash equilibrium, unilaterally deviating, changing your strategy while your opponent keeps theirs the same, will only end up hurting you. Now, this equilibrium builds directly into the minimax theorem. This theorem is the mathematical core of zero-sum games. It essentially proves that an optimal, non-exploitable strategy actually exists. It guarantees that even if an adversarial opponent perfectly learns your strategy and tries their hardest to exploit it, your worst-case outcome is mathematically protected. You are safe.
Finally, we arrive at Section 5, Unbeatable AI Strategies.
Now for the really exciting part, the absolute cutting edge. How do researchers actually translate all of this heavy mathematical theory into deep reinforcement learning algorithms that can play fast-paced video games? Well, first we have to look at why this is so hard in practice. Standard multi-agent algorithms have major limitations. Older methods, like fictitious play, try to treat these sequential, time-based Markov games as if they were simple, single-step normal form games. And the problem there is that the possible action space scales exponentially the longer the game goes on. It creates a massive bottleneck, making these older algorithms incredibly slow and computationally inefficient for complex tasks.
To solve this massive computational bottleneck, the dissertation proposes a really powerful, novel algorithm called Nash-DQN. This is an end-to-end deep reinforcement learning algorithm that finds non-exploitable Nash equilibria directly in Markov games. It elegantly combines the theoretical guarantees of tabular Nash learning with the raw processing power of deep Q networks. By using deep neural networks as function approximators, Nash-DQN can directly handle these continuous, highly complex environments without being crushed by that exponential scaling. It's a total game changer.
And the researchers didn't just test this in theory. They dropped Nash-DQN into 5 different fast-paced Atari games from the Petting Zoo library, as well as the Slime volleyball benchmark environment. But here's the coolest part. To really test its non-exploitability, they explicitly trained a secondary AI called the Nash-DQN exploiter. This was an opponent whose sole purpose was to find weaknesses in the main agent. And guess what? In every single test, the Nash-DQN agent remained completely robust and unexploitable.
I'll leave you with this final provocative thought to wrap up our explainer today. We've just seen direct proof that AI can learn mathematically unexploitable strategies in complex virtual environments. So what happens when these Nash-seeking algorithms move out of Atari games and are deployed in real-world strategic conflicts? Whether it's economics, cybersecurity, or global strategy, how will this reshape human interaction? It is definitely something to think about. Thanks for joining me on this deep dive into the math and strategy of reinforcement learning.